Hi everyone, I'm Professor McBain. Welcome back to Chem 100. This is part 2 of the big and small lecture, and today we are going to talk about the mole and how it helps us count atoms of particular elements. Okay, welcome to part 2 of this lecture series on big and small. So one of the other ways that we need to be dealing with big and small in a chemistry class setting specifically is we need to have a way to describe a certain convenient amount of a chemical. Okay, so that unit is what we call the mole. 1 mole of anything is 6.02 times 10 to the 23rd items of that thing. Why on earth is this arbitrary number useful in chemistry? Well, we're going to get to that at the end, but just trust me that 1 mole of anything is 6.02 times 10 to the 23rd items. You can think of this as the chemist's dozen, okay? So 1 dozen is equal to 12. That's it, right? Similarly, 1 mole is equal to 6.02 times 10 to the 23rd. And so you can have 1 mole of literally anything. You can have 1 mole of sand grains. You can have 1 mole of cats. You can have 1 mole of pennies. But it's much more likely that you're going to have 1 mole of carbon atoms because that's actually a reasonable amount. Okay, so 1 mole of atoms is 6.02 times 10 to the 23rd atoms. This is what we call Avogadro's number. So why do we need to use the mole at all? Well, because atoms are very, very small. If they weren't so small, we could count them 1 by 1, but they are very small, and so we can't just count them 1 by 1. So instead, what we do is, well, we've got this really cool thing called the mole and the atomic mass that help us basically count how many atoms or how many molecules we have there. Okay, so what you do with this mole or with the atomic mass is you measure the number of atoms that you have just by weighing the sample of chemical on a balance. Okay, so for example, let's say that I have 2 gold coins and I weigh them on a balance. Okay, and so those 2 gold coins together measures 62.2 grams. Just as an aside, that the current value of that is $3,098. That's fun. But 62.2 grams of gold doesn't tell us how many gold atoms there are. Not yet, anyway. And so what we need is a conversion factor that is going to help us relate the number of atoms that are present to their mass in grams. And luckily we do, and I'm about to introduce you to it. All conversion factors between 1 mole of a substance and how much it weighs are actually located on the periodic table, and this is called the atomic mass. You might also hear it called the molar mass. Molar because it's 1 mole. So let's take a look. So if you look at the periodic table, this is my favorite version of the periodic table, you'll notice that all of the elements have these numbers at the bottom, right? So you've got the atomic number, right? But then you've got the atomic mass there, okay? So since we're talking about gold, let's hone in on gold, and you'll notice that the atomic mass of gold is 196.967. So let's talk about that a little more. Let's zoom in on it. 79, that's the atomic number, and that tells you that there's 79 protons in the nucleus of gold. Of course, that's the element symbol. It says it aurum, gold. And then this number, 196.9665, that's the average atomic mass of all the different isotopes that exist of gold. Okay, and so we just average them all together, and we say that this is, on average, the atomic mass of gold, all right? And it's in units of grams per mole, okay? So if you have 1 mole of gold atoms, then it weighs 196.9665 grams. So let me reiterate that 1 mole of gold atoms has a mass on average of 196.9665 grams. And so this is where we can turn this into a conversion factor, all right? And so you can write it as 196.9665 grams per 1 mole of gold atoms, or you can even flip that upside down and say that 1 mole of gold atoms per 196.9665 grams. Or you can write it like this, where you have just 196.9665, and then the units are grams per mole, right? Because 197 divided by 1, that just equals 197, right? So then you can ditch the 1. And anyway, the units are grams per mole, right? And so this isn't unique to just gold. This applies to every atomic mass that is listed here, okay? So the atomic mass units are grams per mole, all right? So the atomic mass of beryllium, for example, is 9.012 grams per mole. Grams per mole. It's not grams, it's not moles, it's grams per mole. All right, so back to our gold coin problem. So what we're really trying to get to is figure out how many gold atoms were there in both of those gold coins together. And so it can be tempting to just use a single conversion factor to get from grams to atoms, but we don't have that. However, what we can do is we can figure out how many moles of gold atoms are there first. Okay, so we'll start off with those 62.2 grams of gold, and then we multiply by, hey, wait a second. Wait, no, if we do this, oops, we're going to end up with grams times grams divided by moles. That gives you grams squared. No, square mass does not exist. No, can't do that. Okay, so instead what you do, like I said, you're going to use this like a conversion factor, which you can flip upside down if need be. Okay, so remember, if you're flipping something upside down, then that means that the number itself has to now go in the denominator of the fraction. Okay, so we've got 62.2 grams of gold. We're going to multiply it so that the 196.9 grams of gold ends up on the bottom, and then the 1 mole of gold ends up on the top. Okay, and then this way the grams are going to cancel out, and that's going to leave us with units of moles. Okay, so at least we've gotten from grams to moles. So now how do we get from moles to atoms? Well, we're just going to use Avogadro's number, which applies for every element that exists, no matter, or even every particle that exists too. No matter what you got, if you've got a certain number of moles of something, you always have 6.02 times 10 to the 23rd things in that mole, whether it's atoms or molecules or cats or fluff balls or babies or whatever. Okay, so if we've got 0.316 moles of gold, then to convert that into things, well, atoms of gold, we just multiply by how many atoms are in 1 mole. And so here you can think of the mole as also being a unit, okay? And so we're going to also cancel out our units of moles, and that leaves us with units of atoms, okay? So we multiply that and we get 1.90 times 10 to the 23rd atoms of gold are in those 2 coins. Okay. That's a lot of gold. In general, that is your step-by-step process for converting from grams of an element into atoms of an element. You go from grams to moles to atoms. To get from grams to moles, you use the molar mass specific to the element. And then to get from moles to atoms, you use Avogadro's number, which applies to any element or object that you're counting. All right, here is an example for you. If you're using a pencil to write things down, well, for every letter that you write, you're using about 7 micrograms of graphite from your pencil. So you can also find out how many carbon atoms that is. So you're going to follow a pretty similar process to get this problem done. Okay, but you'll notice that everything is in micrograms first. So the first step for this is actually to convert from micrograms to grams. Okay, so we've got to go back to that slide on the metric system units in order to figure out how to convert between micrograms and grams, but that's no problem. Okay, but so this is always the first step. If you're working with something that is not in grams, you got to get to grams first, period. Okay, so 7 micrograms multiplied by 10 to the minus 6 grams over 1 microgram, that gives you 7 times 10 to the minus 6 grams of carbon. Okay, now we can go about our previously established problem-solving strategy. Okay, so now we're going to be thinking about the atomic mass of carbon, which if you look in the back of your book and you look at your periodic table, you'll find that the atomic mass of carbon is 12.01 grams per mole. Just like we did last time with gold, we're going to flip this thing on its head so that the grams cancel out and we multiply and we get moles as our units at the end. So that gives us 7 times 10 to the minus 6 grams times 1 mole over 12.01 grams. That gives us 5.8 times 10 to the minus 7 moles. Okay, so then the final step is to convert from moles into single items, which in this case again is atoms. Okay, so again we're going to be multiplying by Avogadro's number here per 1 mole, and then that gives us that many atoms of carbon. Okay, so you can also work backwards, okay? So you could ask yourself, how much does 1 billion atoms of silver weigh in grams? And then again, how much does it weigh in pounds? So your problem-solving strategy for this, you're just going to go backwards, but you have to now flip your conversion factors upside down. So if you start with 1 billion atoms of silver, well, you need to get from atoms to moles first. Okay, so it doesn't even matter yet that it's silver that we're talking about. We just need to get from atoms to moles. So again, we're going to use Avogadro's number, but this time we've got to make those atoms cancel out, and we want to end up in units of moles. So we're actually going to be dividing by Avogadro's number. Okay, so once we do that, we're going to get a certain number. Now what I'm doing is a process that we're going to be talking about in our chem activity. This is dimensional analysis, or the factor label method. Instead of going step by step and getting an intermediate answer, you can just say, oh yeah, I'm going to do that. I'm going to do this process, but then I'm also going to show my next multiplication process. Okay, so once you divide your atoms by themselves, this number is going to have units of moles. So then your next step is to now pay attention to the fact that it's silver, all right? So then you're going to go to your periodic table, find the average atomic mass of silver, and since you want to find the mass of that silver in grams first, then you do want to multiply by the atomic mass, just like straight up and down, okay? So you're going to multiply by 107.868 grams per mole, and that gives you, so if you do this, divide by this, times this, that gives you 1.79 times 10 to the minus 13 grams. All right, let me reiterate this reverse strategy. It's the same thought process, but backwards. So if you start with a known amount of atoms and you want to know its weight, you go from atoms to moles to grams. But along the way, you'll still use Avogadro's number to get from atoms to moles, and then the molar mass of the specific element you're working with to get from moles to grams. Notice, though, that whether you're going forwards or backwards, you need to use these conversion factors in such a way that the units will cancel out to result in the units that you want. So some students fall into a trap of thinking like, oh, it's multiplying this way and dividing that way, but it's a really bad idea to try to memorize whether you divide or multiply. And if you try to do that, then you'll probably mess it up on exam day. Instead, it's much better to learn how to use this method of recognizing which units need to cancel out and then setting up your conversion factors accordingly. Because honestly, you guys, I don't even think about multiplying or dividing each time. I just set up my conversion factors and I flip them right side up or upside down depending on how my units need to cancel out by the end of my problem. All right, and then part 2 is how much is that in pounds? So you're going to take that last answer and you're going to look up the conversion factor between grams and pounds, that's 454 grams per 1 pound. But again, we want to end up with an answer of pounds and we want to cancel out the grams. We want to get rid of those. So we're going to multiply by 1 pound divided by 454 grams. That gets us 3.95 times 10 to the minus 16 pounds. That's a very small amount of poundage, huh? Not very much. All right, so like I said, make sure that you are going back to the textbook, the online OpenStax Atoms First textbook, And please be working through more unit conversion problems while you still have those answers available. And then start trying out the homework. All right, good luck, guys.